Take it away. Thank you.
Awesome, thank you. My name is Lucia Perez. I'm a rising fifth-year PhD student at Arizona State University, and recently I've been working out of Goddard Space Flight Center in Maryland because my advisors Sangeeta Malhotra and James Rhodes are on the Roman Space Telescope science team. And today I want to talk about my most recent project, in which I want to share with you different ways of probing patchy ionization using a clustering measurement called the void probability function, and make predictions for the Logger narrowband survey and also for Roman Space Telescope. So as we've talked about this entire time, some of the big questions that still remain about the Epoch of Reionization are exactly when it occurred, what was causing it, and always trying to find new ways to study it and really pin it down. So as we just heard from Axel, Lyman-alpha emitters are a really good probe of reionization because for most of these galaxies, their most prominent emission line is the resonant line of hydrogen. They're very unique and sensitive tracers of any neutral hydrogen in the intergalactic medium around them. So the Logger team, which is a really good collaboration, who you can see at the bottom of the screen, that works between China, Chile, and the United States. A lot of the great work we're doing to specifically tie down reionization and ionization fractions is using luminosity functions. So as the emission from these galaxies is attenuated by the neutral hydrogen, the luminosity function drops and changes shape. And that's a really strong signal. So I want to show you that using clustering, you can measure that signal too in a different way using different model assumptions, and also get a unique signal that comes specifically from the process of reionization itself. Also, I want to hype up Roman Space Telescope. Its field of view is going to be so much larger than anything in space at these wavelengths. And the GRISM specifically will cover Lyman alpha between redshift 7 and 14. And because it's going to have such a deep volume and large area, it's going to be great for doing clustering studies. So I'm really glad I went right after Axel because I'm using the Jensen et al. 2014 and 2013 simulations to do this study of how the void probability function can do this work. And thanks to the team, I know some of you are here who have shared your simulations with our team. But these are simulations of 600 co-moving megaparsecs on each side that have been evolved through reionization. And depending on the ionization fraction, they have at least 1 million Lyman-alpha emitters within them. And I can give more details about this, but I'm going to focus specifically on how we can use these simulations to measure clustering and get an idea of the true value given our knowledge and assumptions, and also get a sense of any fundamental external errors that might exist. So what I do with these simulations is I make little experiments. So first, we can cut up the large volume into little slices that mimic what Logger will see. So the narrowband survey using DECAM on Cerro Tololo sees 3.3 square degrees and a single viewing, and the narrowband covers about 30 co-moving megaparsecs in redshift space. So we can get 320 little slices to mimic a single Logger field. And then for the Roman Space Telescope, based on work that's being done by Isaac Wald with simulations, based on the fundamental limit that we think the GRISM will have, we imagine first just a square degree in the sky between redshift maybe 7 and 8 with a redshift depth of 0.5, which ends up really conveniently being little cubes of 150 co-moving megaparsecs on each side. So we can get 64 little test volumes to get a sense of what individual Roman Space Telescope fields might be able to do with this measurement. So my clustering method of choice is the void probability function. It's a really simple measure of clustering. You just ask if you drop a random sphere for 3 dimensions or a circle for 2 of a given size, how likely is it to be empty in your distribution? The VPF is really sensitive to number density, and we know the VPF of random distributions theoretically. And part of the work I was doing for the first couple of years of my grad program in a paper that's in the final stages of review is thinking about how we can use the logic of the VPF to get a sense of when your clustering measurements can be trusted, and also to make predictions. You might need this many galaxies and this kind of volume to get that measurement. So keep an eye out for that in the next couple months. So I alluded before that there are 2 different ways that clustering carries the signature of reionization with Lyman-alpha emitters. So the first way I'm kind of clumsily calling the single luminosity cut method. So we imagine a detector that has a fundamental limit for what it can see. So as you're detecting Lyman-alpha emitters farther back in time and more neutral IGM, you see fewer because it's getting more neutral. So we see this as we compare 95, 50, and 30% ionized. And you can see that at 30% ionized, the most neutral, the number density has dropped a lot and they appear more clustered. And this is a really strong signal. The luminosity functions that Isaac Wald is going to publish soon are showing this really clearly. And even Wade who saw it in 2013 with the logger 2 fields. It's a really strong signal, and we'll see this very clearly with the void probability function. But this signal includes not only the effect of reionization, but also that maybe dark matter halos are merging themselves. But the second method we can do is taking advantage of the fact that we think that reionization is an inside-out patchy process. So Lyman-alpha emitters are more likely to be observed where the intergalactic medium has already been ionized. So if you imagine 2 distributions at different different ionization fractions, sorry, but you hold them to the same number density, the more neutral one will appear more clustered. So you can see this as I flip between 95 and 30% ionized. And this is a really subtle signal that, again, is a signature of patchy inside-out reionization. And I'm going to say that if we're ambitious, Roman Space Telescope will clearly be able to tell the 2 ionization fractions apart and give a completely different constraint for reionization. So let's do the measurements on these simulations. So the VPF, again, is a fraction that you measure at a given radius. So on these plots, the dashed lines are the VPF of a random distribution at that given density. And here we see what happens when you have a single luminosity cut that leads to different number densities. And the dots are the measurements of the VPF for the different ionization fraction versions of the same volume. And as you can see, each of the lines is really separated out from its own random distribution, which is great and expected. And they're really separated out from each other, even when you have some errors thrown in there. So again, we'll go into more detail of how we can see this with logger and WFIRST. But let's look at also next, the single density cut. Again, this is the really ambitious measurement that's a totally different way to measure inside-out patchy reionization uniquely. And as you can see, even when we use the whole breadth of our volumes, they're still going to be kind of hard to tell apart. So to explore how viable both of these measurements will be and to make predictions for these telescopes, let's zoom into a single radius first. The VPF is a volume average correlation function, so you can kind of take one radius and run with it. So first prediction, can logger measure the ionized IgM fraction with its 4 fields? So if you remember it, I cut up the volume into 300 little slices to mimic what a single logger field sees. So what we can do is I randomly choose 4 of these slices. I measure the VPF of each of them and then average that value together, with the hope that as you sample more of the larger volume, you get closer to the true population mean. And I repeat this process tons of times, so then we can see how the average of those 4 changes as you vary this. And as you can see with the single luminosity cut here on the left side, the 95 and 30% ionized have distributions that are really separated. So we'll be able to complement and constrain and help out the luminosity function analysis that our team is doing with the clustering measurement of the Lyman-alpha emitters once that becomes available. And then we can see with a single density cut, I warned you, this is a really ambitious measurement, and it might be rough to do from the ground. And even though luminosity cut is incredible, it's a different way of constraining it. Let's be ambitious and think about how can we get that signature of patchy reionization done. Let's look at the Roman Space Telescope. So how does 1 square degree do? Again, we see that with the single luminosity cut, the distributions are quite separate. The bending isn't the neatest here, but it's okay. And again, with the single density cut, it might be hard with 1 square degree. So you can ask me, how many square degrees does Roman Space Telescope need to do this really difficult measurement? And the answer is 4. So you can see with 4 square degrees, the 95 and 30% ionized become really separated. And of course, this is a very ambitious measurement. The luminosity functions cuts with the single luminosity cut will already be quite ambitious and do a great job. Thank you all so much for listening. Again, clustering can be a different way to complement our different methods of measuring ionization fractions. Yeah, thank you so much.
Thank you very much, Lucia. So we've got time now for questions.
And something I can say while these roll in, when the VPF of your given sample is measured, as long as it has very similar luminosity cut or number density, you can directly plot it on this and get an estimate for the ionization fraction based on the Jensen et al. 2014 simulations and their assumptions. Oh, great. I'm sorry, I have the Slack open right now. Do you want to read
those
the
things are popping up. Yeah. So actually, this is one question that I had as well. So from Fred Davies, how does the void probability function compare to using the angular correlation function in terms of how well reionization can be constrained?
That's a great question. So no one else has done the VPF with reionization yet, so I won't be able to answer that question until we get it done with observations. In terms of the theoretical side, McQuinn et al. 2007 made predictions for the angular correlation function. And it will do it well, like all the clustering methods will carry the signal with it. So that's still a question that's open of how well they can do. The other thing to consider is that samples of Lyman-alpha emitters above redshift 6 are very hard won and like really carefully tended. And especially with clustering analyses, you need a lot of galaxies. So this is something that only now is really becoming viable to do with like really, really good error bars. And I know that like a lot of teams have done really good work and constraining this. I know, oh my goodness, the name, it's a K-name 2006. They did the VPF of Lyman-alpha emitters at redshift 6.6, and that had a constraint. But they only had like 47 Lyman-alpha emitters because it was 2006. So it's an ongoing process. Good question.
Yeah, non-detection. So more of the what we're looking for with Lyman-alpha emitters at these redshifts. Okay, so the question from Steve Finkelstein, who says, who asks, how deep do you need to go in line flux over this 4 square degrees for this measurement? Could you go deeper over a smaller region and get the same distinction?
Oh, excellent question. So the line flux limit I used is one that Isaac Wald recommended to me based on his WFIRST simulations, and that's 10 to the negative 17 ergs per second. And for the single number density, we ran with just what Logger is observing right now and also corresponds to what the WFIRST simulations are seeing. I think, yes, you can go deeper over a smaller region. For sure, because the VPF like clustering measurements in general, like if you can get really, really good dense measurements, then that decreases your error. So for sure, I'm not sure exactly how much, but that's a really great question we can explore. Thank you.
Okay, and then a question from Fahad Nazir, which is, I guess, a bit related to Fred's question, but have you tried methods other than the void probability function?
I personally have not, but Jensen et al. In their 2014 paper do this with count in cells, and they show that difference. But I will say that they specifically focused on the single number density cut method when they showed their count in cells, but it would be a very, very strong signal with the single luminosity cut too.
Okay, and then I can't see more right now. So I actually have a question too. I guess, I don't know if I missed this right at the beginning, but could you talk a bit more about the model that you use for the Lyman-alpha emitters themselves and whether that like evolves with redshift?
Yeah, so this was a lot of great work that this whole team did for several years. So I have some summaries here. I have slides that can tell you a lot more. If I remember correctly, and feel free to correct me in the chat for those who worked on this, I think if I recall correctly, they had like a single shape. I'm sorry, this is like a little like rough in my memory. I think the biggest thing with the line, I don't want to speak too much and be wrong because like this was a lot of really careful work they did. But yeah, the biggest thing was that they simulated the observed Lyman-alpha emission as it emerged from the galaxy and then as a separate step as it went through the IGM. So I will leave this here so then folks on the YouTube can read my summary of this and pause on it. But that's a great question. Yeah.
Okay, thanks, Lucia.